Hello everyone, welcome to Code Enzyme. So this is the 19th video of the series Graph Algorithms for Competitive Programming, and in this video we are going to discuss about Eulerian tools. Now I don't know how to pronounce it, is it Eulerian or Eulerian? So I feel comfortable with Eulerian, so I will pronounce it Eulerian, okay? Now kindly correct me in the comments if I am wrong. So first of all, in this video I will talk about the undirected graphs only. So for directed graph also it is pretty much similar, but I think I will cover it in the next video, okay? Now, first of all, this is defined for finite graphs only. So this is only defined for finite graphs. Okay, let's get into the definitions now. So first we have what is a Eulerian tour, or it is also called a Eulerian path. Now, this is defined as a trail that contains every edge exactly once. Okay, so suppose you have a graph, let's say, so suppose we have a graph, and what could be a Eulerian tour of it? So one possible Eulerian tour can be 2. Then let's go to 1. So we have covered this edge. Then we can go to 3. So we have covered this edge. Then let's go back to 2 again. So this edge is also used. Then we can go to 4. This edge is also used. And then we go back to 3. So by this traversal, we have covered all of the edges. Okay. Another Eulerian tour can be, so this is not unique actually. Like you can have several kinds of Eulerian tours. Uh, let's say you can start from, we can also start from 3. Let's go directly to 2. Then we can go to 1. So we have used this edge, then 3 again. So we have also used this edge. Then we can go to 4 and then 2. Okay. So a lot of Eulerian tours are possible. So basically we are starting from one node and we are ending at other, such that we are using all of the edges. Okay. So this is called a Eulerian tour. What is a necessary condition for such a tour to exist? Like if I ask you, can you have a Eulerian tour starting from 1? So let me erase everything. So my question is, can you have a Eulerian tour starting from 1? Let's try. If we choose 3 as the first index, then if I go to 2, then I will remove this edge. Then I can't have a Eulerian tour, right? Because if I choose 1 directly, then I can't use this edge again, and if I go this way, then I can't use these two edges. Similarly, I will not be able to choose 2, right? So we can't have a Eulerian tour starting from 1. Similarly, we can't have a Eulerian tour starting from 4, right? Because this graph is symmetric, then I can say that it is not possible. So what is the condition? Like how do we know that a Eulerian tour is possible or not, and what are the starting and what should be the starting and ending nodes? So the necessary condition is every node should have even degree except 2 nodes, the start and the end nodes. Okay, so in this graph, if you see, this node has even degree, this node has even degree, and these two nodes have odd degree. So I can say, okay, a Eulerian tour exists, and these two can be the start and the end nodes, and that way a Eulerian tour will exist. Now it is a common sense, like you can try proving it also, because every node, because one of these will be the end and one of these will be the start. That is why we have we have these two the odd degree. Otherwise, if you see, one node will be used for incoming and one node will be used for outgoing. So even if you have multiple edges, like let's say we have something like this, and let's say I add 2 more edges. So if I talk about this node, then one edge can be used as incoming node and one edge can be used as outgoing node. That is why we have even degree nodes in between edges. Okay, and the start and the end nodes are start and end. So we will have one edge separately for only outgoing and one edge separately for incoming. That is why we have 2 nodes as odd degree with odd degree. So that is the only necessary condition to have uh, a Eulerian tour. Also, the other condition would be that this whole graph should be connected in one. So this whole graph should be one single connected component. Okay, so whole undirected graph should be single connected component. So I hope this is clear. Like how do we find Eulerian tours? So finding Eulerian tour is not tough. Like let me just erase it. Okay, let's say we have something like this. So one, this is 3, and this also has 3. This has 2. Okay, so one of the possible Eulerian tour can be, let's choose this. Then okay, let's go this way. Then what I can do is now I don't want to go this way. Yeah. So this is one of the possible Eulerian tours. So we have 2, 1, 3, 4, 5, 2, 3. Yeah. 2, 1, 3, 5, 4, 2, 3. Sorry. 2, 1, 3, 5, 4, 2, 3. So this is one of the possible Eulerian tours, and this is how you find it. Now I will discuss the algorithm later to actually finding such Eulerian tours. But these are the necessary condition that a Eulerian tour actually exists. Okay. So now you know about Eulerian tours. Let's also talk about Eulerian circuits. So a Eulerian circuit or a Eulerian cycle is a Eulerian tour which starts and ends at the same index, which starts and ends at the same node, right? So I mean, let's discuss a case like what are the possible Eulerian circuits. So let's consider a graph. Now we want to start and end at the same node. So one possible way would be, so let's start from 1, and okay, so let's consider this as 2. Then I can go 3 also, but okay, let's also consider some other cases, like let's first go 6. I mean, okay, let's go 3 only, because I don't want to contradict that, it might not be possible. Now uh, now let's go 5. So 3, 5, then 4, then 2. After 2, let's go to 6, then 3 again, and then 1. Okay, so this is one of the possible Eulerian circuits. I'm starting at 1, ending at 1, and I have visited all the edges. And one thing you will realize that once I do that, once I have assigned all these edges, this graph becomes strongly connected. This directed graph that I have formed is strongly connected graph, strongly connected directed graph. And this whole is a single strongly connected. So this is a single. This whole thing is a single strongly connected component, and it is representing a directed graph. So if someone gives you an undirected graph and tells you that assign directions to these edges, and you have to assign these edges such that the whole graph becomes strongly connected, then this is the solution. You have to check if you will have to check that if that undirected graph has a Eulerian circuit or not, and if it has a Eulerian circuit, then you can try forming a strongly connected in this way. You can orient these edges like this, and this kind of orientation is called a Eulerian orientation, or we can also call it Eulerian oriented graph. Okay, so I hope that is clear what Eulerian oriented graph is. When you assign direction to these edges, it becomes Eulerian such that when you assign direction to these edges such that you can start from a single node and end at the same node, this graph becomes Eulerian oriented graph. It is a directed graph, and it represents a single strongly connected component. Okay, so I don't want to repeat the same thing again. If you want, so if you don't understand something, kindly rewatch a few minutes from before. Okay, now let's continue. So let me erase everything again. Okay, now let's also discuss the necessary conditions. Now there is a single necessary condition is that all nodes should have even degree. I think this much is clear. Now let's see a problem and let's try to solve it. So the problem that we are going to discuss is the CSES problem, mail delivery. Now let's first read the problem statement. Your task is to deliver mail to the inhabitants of a city. For this reason, you want to find a route whose starting and ending points are the post office. So you are starting from the post office and we are ending at the post office. So this is not asking for a Eulerian tour, it is asking for a Eulerian circuit. And that goes through every street exactly once. Okay. Now the input format is, first line has two integers n and m, the number of crossings and the number of streets. The crossings are numbered from 1 to n and the post office is located at crossing 1. After that, there are m lines describing the street. Each line has two integers a and b, the starting and ending point of the streets, and all the streets are two-way streets. Now every street is between two different crossings, and there are at most one street between two crossings. Okay. Now print all the crossings on the route you visit them like that. Okay, so we just need to print the Eulerian tour of the city, and we have to start from, I think the post office was at index 1. Yeah, so we want to start from 1 and we want to end at 1. Like we want to start from the post office and end at the post office, and we want to print all the nodes that we encounter in between. Okay, so how do we actually calculate it? Now there is an algorithm for finding the Eulerian circuits, and this algorithm is called I don't know how to pronounce it. This is from Wikipedia, so you can also search for it here. You can search for Eulerian paths and you will arrive here. Okay, so in on the Wikipedia, if you read it, I won't try to pronounce it because I know I will not pronounce it correctly. So let's just read about it. We choose a starting vertex V and then follow a trail of edges from that vertex until returning to V. So I think I will just try to dry run it in on a test case. So the test case from the CSES problem looks something like this, right? So the algorithm says let we choose the starting vertex V and then follow a trail of edges until returning to V. Okay. So I can choose any trail of vertices, like I can choose this path to this path and to this path also, or I can even choose this one. I mean, whichever path we prefer. So let's actually choose this one. Okay. So currently it looks something like 1, 2, 6 and 3. Okay. Now it is not possible to get stuck at any vertex V other than V, because all the edges have even degree and it ensures that the trail enters another vertex W. There must be an unused edge leaving it. So that is that. Now the tour is formed is a closed tour but may not cover all the edges initially and the edges of the initial graph. So it is a closed loop, that is correct, but it may not cover all the edges. Okay. Now there is a second step. As long as there exists a vertex U that belongs to the current 2 that has the adjacent edges not a part of the 2. So we have two nodes like 3 and 2 that have edges that are adjacent to them and it's not a part of this current 2. So we have to choose them before going to 1. So before going using this edge, we should choose them, right? We should choose them. So right now our tour looks something like this: 1, 2, 6, 3 and 1. Okay. Now it says that when I'm going, I should choose the edges that are not used. So before going to 1, what I should do is, okay, I will keep 1 at the last, and now I should choose some other trail. Let's choose I mean I can go either choose 2 and either choose 3, either choose 5. So I have marked these 4 edges, so let's choose 2 only. So let's say I go to 2, then 2 has some edges that are not marked, 4, then 5, then 3, and now all the edges are marked, and then I go to the next edge, that is 1, right? So this is the algorithm for finding the Eulerian tours. Okay, so I think it is pretty clear and easy to implement also. You just need to keep a check of how to. I think the difficult part would be how you actually store it and how to mark the edges, right? How to mark. So you will have to store the edges in such a way that you are able to mark them. And this same implementation, I mean, I won't say same, but similar implementation is used in the flow problems to mark the capacity of the edges and all. So kindly learn this algorithm very carefully of how to actually store them. Now let's actually read further. By using a data structure such as a doubly linked list, we want to maintain a set of unused edges incident to each vertex and to maintain a list of vertices on the current 2. So we want to maintain a list of edges in the current and unused edges. So something like a linked list implementation. So yeah, I mean, I can have a graph of an adjacency list and try to pop them, but I mean that will also pass. I have tried it, so I will also show you that kind of implementation where you can maintain an adjacency list and try to pop the elements as they pop the edges that are used and that are marked as used. But I think that is a bit inefficient because you are popping something, so even if it is O of 1, it is actually amortized O of 1. It might not be exactly O of 1. So what we can do is we can maintain pointers, like for every edge we can maintain where it is pointing towards next, what was the head of it, and which element am I currently at. And like that, I think it will be more efficient. So I will just show you both the implementations. And this time also I will not be coding it because I feel that I think it is a waste of time, me just trying to code it up, and I'm not sure how many people are actually watching this video. Okay, if you prefer that I should code it in the video, then kindly tell me in the comments. From next time I will try to code it myself. Okay, now let's see the code. Okay, so first thing first, I am taking the n and m, then I'm maintaining two things, like the head where it is pointing. For the nodes, like currently, like at what index I'm starting, the head will obviously point towards, like the head, it is the start index of the edge. Like for every edge I'm maintaining an index. What is it currently at? I think you will better understand if you try to type it, or type it yourself, and when you implement the DFS function, you will get to know why I'm doing it. Okay, so first I'm maintaining a head, and the next pointer. Like I don't know how to actually explain this. I think okay, let's say you have a count. Let's say I have a count. Like I'm starting the count for every edge. I am assigning it an index. Okay, and that index, actually I'm assigning it two indices. Like the first edge is given two indices, 2 and 3. And why I am doing it, it will get clear when you implement the DFS function. Okay, so and I also need to check that if every node has even degree or not. For that, whenever I have a graph, I will check that I will increment the degrees, and then I have to check that, okay, if the degree is odd, then it is impossible, because all the nodes should have even degree, right? Now once this is done, I am marking these things, like okay, for every edge I am marking that this edge is pointing to V, and uh, and this edge is also pointing to U, like that. And you will notice here that with this implementation I don't even need to have an adjacency list. I don't even need to store what is the graph of node.next and all. Now once this is done, I am maintaining this, like okay, obviously I have to say that current of I is the head of I. Now I also need to maintain a bool variable of mark. So if the edge is already marked, I don't have to use it. Okay, and the final answer will be stored in this vector called paths. Now okay, so I will traverse in all the nodes, and after something is done, like after I'm done traversing, then only I will add the node at this end. And by this step you will realize that why I stored every node as the two indices. Like this will mark as the forward edge, and this is the backward edge, because we have an undirected graph. Like first index is at 2, right? First edge is assigned 2. Now 2's or 1 is 3, so that is equals to count plus plus. Like for the even index, let's say we have the second index is stored at 4, then that the back edge will be stored at 5, which is equals to 4's or 1. So that is why I'm setting the both equals to 1. I'm marking them as 1 like this. And then we are doing DFS2. Where was this edge pointing to? At that node I'm going. And after this is done, I'm traversing in the I'm saying that okay, let's append it to the path. Okay. So the same thing, like we went to the first, but I did not want to add 1 directly. First I wanted to traverse in the path of 3 wherever I could go, and after that I will add it to the path, and that's it. In the end, just check if the size is m plus 1. That means if the whole graph was connected or not, because you might find a Eulerian tour but the graph might not be connected, and then we have, if that is the case, then we need to print impossible. Also I think this is pretty much clear. I will give the link of this code in the description, or maybe in the pinned comments below, so you can check that out. Okay, so I hope you were able to understand this. Let's also see another version of this code. So I will also give the link of this code in the description or in the pinned comments, so you can try to read this up. And this is basically the reverse of this implementation. In here we already had the degree, and in this code we are trying to add edges one by one. So I'm incrementing the degree one by one. So you can also check this out. I think this is more simpler. I mean, both of them are pretty simple. I think both of them are similar. You can just try to read it out. Okay, so I hope you enjoyed today's lecture, and if you did, kindly like this video. Tell me in the comments if you are liking the series or not. There are not many videos left, so kindly tell me in the comments if you want something new, like should I make a one on tree algorithms or not, or maybe I can do one for dynamic programming and all. Okay, so I will see you guys next time. Thank you.